Hello and welcome to today's session. We're looking at black holes. We have two objectives today: to know how to define the event horizon for a black hole and to know how to calculate the Schwarzschild radius for the event horizon of a black hole. So to recap, we looked at classifying stars by their spectral class. Then we moved on to the HR diagram, where absolute magnitude was plotted against spectral class, and from that we could see where stars were on their life cycle. And larger stars, much larger stars than our sun, could end up as a neutron star or black hole, with smaller stars ending up as a white dwarf. And we said that you need to be able to sketch the HR diagram, and it's usually worth 3 marks. So you need to have a scale for absolute magnitude, a temperature on the x-axis. Sometimes they ask for the spectral class as well. And you also need to be able to just label that diagram for the main sequence, white dwarfs, giants as well, just where they are positioned on that HR diagram. So today we need to look at black holes, and in particular the Schwarzschild radius, and think about what this means for the center of the galaxy. So the center of the galaxy for us in the Milky Way, based on observations of stars close to the center of the Milky Way, we think there's a massive or supermassive black hole. So we need to look at black holes today. So we can't directly observe a black hole, and what you've got here is an artist's impression. So we've got the event horizon, that's the radius around the black hole, and we've got an accretion disk. What we say that is all the matter and dust that's around the black hole. So we can observe indirectly the matter that falls into the black hole, because radiation is emitted in the accretion disk, but we can't directly see the black hole. And we can also observe the stars that are orbiting a black hole. So as I said earlier, the supermassive black hole that's thought to be at the center of the Milky Way. So those stars have much higher orbital velocities, so we think that there's a massive black hole, supermassive black hole there, that's responsible for that. So not a direct observation, but indirect observation, and that is what we work with, the idea of indirect observation, and you've got a disk, accretion disk around. That's the idea. So I've summarized that in these 3 points, and I've said, well, we've got these stars orbiting an invisible center of mass, and thinking about the Milky Way galaxy. So if we were trying to define a black hole, we could say it's a region of space-time that has such a strong gravitational field that no particles or electromagnetic radiation can escape from it. We also need to define the event horizon and the Schwarzschild radius. So the event horizon is defined as a boundary at which the escape velocity is equal to the speed of light. So matter within the event horizon cannot escape. No signal can get out. And at the center of the black hole, we have a singularity where the density is infinite, so nothing can escape. And the Schwarzschild radius is the radius of the event horizon. For the exam, you're given the equation for the Schwarzschild radius. Over the next couple of slides, I'll show you how we get to that, and we think back to gravitational fields. So going back to gravitational fields, we think about an object of mass m. So you can imagine that object that's within the event horizon, and then the massive object of capital M, which would be the actual black hole. So we think about it in terms of kinetic energy and gravitational potential energy. Equating those two together, we can get an estimate for the Schwarzschild radius. It's given to you on your formula sheet, as I said, as RS is equal to 2gm over c squared. G is the gravitational constant, that's on your formula sheet. M would be the mass of the black hole. So in questions you'll be given the mass, so it might say it could be 20 solar masses. C, speed of light squared. Obviously RS is the Schwarzschild radius. So it's on your formula sheet, but we'll talk about how we get to it over the next couple of slides. So we know kinetic energy is half mv squared, and from gravitational fields, the gravitational potential energy on the surface of a more massive object m is gmm over r, so minus gmm over r. And at infinity we define the gp as 0. So this goes back to gravitational fields. What you'll see is we'll equate these two together and find a relationship for the escape velocity, and then use that to find the Schwarzschild radius. So again, the formula is given to you, but I know some people want to know how do we get to it. So these are the relationships we use. So for the escape velocity, we think about the kinetic energy loss equaling to the GPE gain. So we always talk about a transfer of energy. So even in year one, where we did work, energy and power, we talked about transfers of energy from one form to another. If we think about the mass taken to infinity, the difference in GPE, difference between those two positions, 0 minus our relationship for GPE, so minus gmm over r, gives us the GPE gained. So we equate that to the initial kinetic energy. And you've done escape velocity for an object on Earth. It's exactly the same process, but we just think about what's happening if we take an object to infinity. So exactly the same process. Half mv squared is equal to gmm over r. So we've done this before, but we're just trying to extend it to thinking about a black hole. So make V the subject. So all we do is make V the subject. So rearrange, make V the subject. The escape velocity from our definition for the Schwarzschild radius is the speed of light. So V is c. We change r to rs for the Schwarzschild radius, and this is our escape velocity for the event horizon. Then to make the final step, or to get to the final step, which is on your formula sheet, rs, the Schwarzschild radius, just make rs the subject, and that's what is on your formula sheet. So that's how we get to that relationship. Okay, so that brings us to what's given on your formula sheet. So you can see we just equate kinetic energy and gravitational potential energy and make some assumptions, and we can get to a value of the Schwarzschild radius, so an approximate value of the Schwarzschild radius. Typical questions, which we'll go through on the PowerPoint, on this PowerPoint, is to calculate the Schwarzschild radius or to calculate the density of a black hole. So we'll look at that. We know the density of an object is given by mass over volume. Assuming that the black hole's a perfect sphere, then we can say the volume is 4/3 pi r cubed. And then all you'll need to do is substitute in the equation for the Schwarzschild radius for r into that expression, and then you can find the density. As I said before, at the center of the black hole, density is infinite, so it's not uniform density across this black hole. At the center it's infinite, and we call that the singularity at the center of the black hole, so where the laws of physics sort of fall apart. Okay, so you can see a typical question here. Calculate the density of a black hole with a mass equal to 20 solar masses. On your formula sheet, you're given the solar mass of the sun, so it's given to you on the front page, 1.99 times 10 to the 30 kilograms. You're given the equation for the Schwarzschild radius, so 2g m over c squared, and we know that the density is mass over volume. So all we need to do is find the radius, so substitute into the equation, then calculate the density. So we'll do that on the board. So first of all, we'll find the Schwarzschild radius. So RS is equal to 2 times g. So g is a gravitational constant. That's on your formula sheet as well in the first bit. So 2 times 6.67 times 10 to the minus 11. And it's 20 solar masses. 20 times 1.99 times 10 to the 30. This is all over c squared. So c, speed of light, squared. So I put that into my calculator. I get a value of 58,992.4. What I'll do is I'll round values at the end. So at the end, I'll go to 2 significant figures because that is the lowest amount of precision we've got in here. Speed of light's to 2 significant figures. We do have the gravitational constant, that's to 3, but we'll go to 2 significant figures. Okay, then density rho is mass over volume. Remember, we're assuming that the black hole is perfectly spherical, so you've got the volume of a sphere on your formula sheet. So again, put the mass in, 20 solar masses, divided by the volume, 4/3 pi r cubed. That gives us a density of 2 significant figures, 4.6 times 10 to the 16 kilograms per meter cubed. So we can see that's a very high density, very high density. If we were to compare it to like a neutron, so if you think about one neutron on its own, it'd be about what, in the order of 10 to the 16, 10 to the 17. So very high density. And then as we said earlier, as I said earlier, at the center of this black hole, the density is infinite. So that singularity where the physics just breaks down. So you can see what we need to do in these types of questions. You're given the Schwarzschild radius. Sometimes you have to find that in a particular question. So you've got that formula on your formula sheet, and you might also be asked to find the density. So density is mass over volume. For the values of the solar mass is on your formula sheet as well. So you're expected to just go to your formula sheet and pick out the key values. Okay, so your task is to complete the black holes exam questions and then submit that via Turnitin. So there are a few past exam questions for this topic, and you'll see much in the same way as this example I went through. You need to find the density, you might need to find the Schwarzschild radius. You can also be asked to define the black hole, the Schwarzschild radius as well, and then they'll link it to telescopes as well. So you can have quite a content-rich question with the black hole stuff at the end, or it could be linked to stellar evolution, and then you might have a black hole section as part of that question. So do this task, complete it, submit it via Turnitin, and as usual, if you've got any problems, drop me a message on Teams or send me an email. I will get back to you. Right, guys, thanks for listening, and I will see you next time.